Hi, we are from CE1 Group 10 and we will be presenting about our integrated design project for the January 2021 semester for the subject Reaction Engineering I, Process Modeling and Simulation, and also Separation Process 2. The members for the team are Azmeesa Teh, Chicamba Tainara, Darrence Paulus, Syaidatul Arfah, and lastly Wong Yi Lin.
As per requirement of this project problem statement, we are to design a reactor separator system for the conversion of 3,000 tonnes per year of pomade to produce biogas with high quality involving the anaerobic digestion processes.
Let's take a look at the Reaction Engineering I part. The proposed type of reactor for the process is CSTR. As you can see on the figure, this CSTR is arranged in series. Since pomade contains high solid content, CSTR is the suitable reactor as it can withstand high solid contents without affecting its efficiency. Other than that, CSTR also provides good contact between pomade and the microorganism. This will increase the yield of the biogas. The proposed hydraulic retention time is 14 days. Some research have found that at this value of HRT, it yields the highest amount of methane. Pomade contains various components, but we only consider carbohydrates involved in the anaerobic digestion process. As the pomade is discharged around 80 to 90 degrees Celsius from the processing plant, the fats and protein will be degraded. Phosphorus is removed by denitrification, nitrification, and phosphorus accumulation process. And potassium, magnesium, and calcium are considered as inert and will not be involved in the reaction process. After doing calculation using the value that we have set for the process and the type of reactor, the volume proposed for the reactor is 1,318.15 m3 for each CSTR.
Moving on to the conditions of the reactor which need to be optimized to ensure high production of biogas, which are firstly the temperature, which must be at 46 degrees Celsius as it is a mesophilic range and the best temperature for the bacteria to react. Next, the pH, where it is acidic at pH 5 and neutral at pH 6.85 for CSTR1 and CSTR2 respectively. Last but not least is the catalyst that are needed to increase the rate of the reaction, where enzymatic hydrolysis is chosen for the first reactor and ion nanoparticles for CSTR2. For the last part of the Reaction Engineering I, in order to improve the yield and also the selectivity of the reaction, few enhancements need to be done, which firstly, the pre-treatment of pomade to improve its microbial activities, that also work the same as the addition of catalyst as mentioned before, and also to add a recycle stream to increase the conversion of the overall reaction. Other than that is the temperature alignment should be frequently observed as to ensure it always in the optimum range. Lastly, by adding trace elements, for instance nickel and also zinc, that will enhance the selectivity of the methane formation.
For the process modeling and simulation part, a model was developed as to determine the values of each component. Our main objectives are to develop a model that enables the determination of mass balance, to develop a model that enables the determination of species concentration profile, and to develop a model that enables the determination of temperature inside CSTR. There are a few assumptions that we consider before developing the model, such as reactor is well insulated, which means that the heat loss from reactor to environment is small and destined to be negligible. The reactor contents are perfectly mixed and do not exhibit significant gradient of species, concentration, or temperature in any part of the reactor. No work is done. It is an irreversible and steady-state reaction. The kinetic energy and potential energy are equal to 0. The heat capacity is constant at operation temperature, and the overall heat transfer coefficient is constant. While developing the model, these formulas were used to start our model: mass balance, component balance, and energy balance.
After we substitute all of the formulas, we combine the mass balances with component balances to find the rate of reaction. Then we use the model to find the values. We also use the software Aspen HYSYS to simulate our reactors to obtain the result. And then we compare the results with our manual calculations. For example, the mass flow rate of CSTR1, the manual calculation shows 26.01 kmol per hour, and the HYSYS 23.969 kmol per hour, and the percentage error is 7.85%. For the CSTR2, manual calculation is 39.882 kmol per hour. HYSYS 42.02 kmol per hour. The percentage error is 5.36. The results from manual calculations are slightly different from the simulation. This happened because the assumptions in the manual calculations may not exactly the same as the simulations. We also use values from articles and journals, so the results became varied. Overall, the manual calculations is assumed to be accurate. That is all from process modeling and simulation part.
For separation process 2, we are going to eliminate water vapor, H2S and CO2. Water vapor is crucial to be removed firstly, as it can cause corrosion due to the reaction with hydrogen sulfide and CO2 to form acid. Besides, condensation or freezing of water due to high pressure and accumulation of water in the pipes may occur. Thus, it will negatively affect the performance of every separation unit. Next, H2S removal is important because it will cause odors, equipment corrosion, and sulfur emission when the gas is burned, and it is very dangerous for human and animal health. Meanwhile, the presence of CO2 in biogas will result in reduction in calorific value, so it's necessary to be removed. The inlet biogas is pressurized and led through the adsorption column filled with the silica gel. H2O molecules adsorb bed adhere on the silica gel. Then, moving on to the H2S removal, the biogas will enter the adsorption column filled with alkaline impregnated activated carbons as adsorbent. It modifies and enhances the adsorption performance by increasing the number of active sites on the adsorbent surfaces. Hence, H2S can be efficiently chemisorpted. In addition, a recycle stream is introduced in order to increase the efficiency of H2S removal. Moving on, the biogas is passed through two membrane separator units to remove CO2. The membrane that we select is mixed matrix membranes composed of polyimide and metal organic frame wood (MOF). At here, the fixed stream contains CH4 and CO2. For biogas upgrading, CO2 permeates through the membrane as permeate, while CH4 retains on the inlet side as retained. Firstly, advantages of choosing silica gel as adsorbent is because they are cost-effective, non-toxic and non-corrosive. Besides, regeneration of silica gel can be easily achieved by evaporating the water through decompression and heating. Secondly, some advantages of adsorption process is low operating temperature, low energy consumption, high loading capacity, and high adsorption efficiency. The most important thing is impregnated activated carbon can remove multiple contaminants such as the H2S, silicon, and water. Furthermore, membrane separation has lower energy consumption, good selectivity, easily engineered modules, and therefore lower the cost. Last but not least, MMAS combine the high structural properties of inorganic membranes with good permeability and mechanical properties of polymers. So, we are now come to conclusion. For Reaction Engineering 1, CSTR is used, cellulose enzyme and iron nanoparticles are chosen for CSTR1 and CSTR2 respectively, and the selected values are 5 and 6.85 for CSTR1 and CSTR2 respectively. Meanwhile, for process simulation and modeling, the students are able to determine the complete mathematical model and run the Aspen HYSYS simulation software. Lastly, for separation process 2, water vapor, H2S and CO2 are removed.
During the execution of this project, we have learned to design a reactor separation system with the optimum conditions and also properties. We also learned how to simulate the design on the HYSYS simulation. The integrated design project is a very good experience for us as the future engineer and as to work in a team because we're going to work in the same environment again. And as for improvement of the overall project, if we have more time, we could have find another alternative in reducing the percentage error and also to enhance the overall integrated design project.
That's all from us. Thank you.